Now, there are several ways of solving this. I'm using one of them, which is, it's not really very compact, but as compact as possible. So, first idea, I use the product rule inside the component-wise differentiation. And in order to do this, I prepare myself by firstly differentiating this scalar prefactor, as you've seen here. Okay, this one. I take the derivative of this one first to use it later within the product rule. And then, well, this is quite well known because have we already? No, we haven't. But okay, this is component-wise to be differentiated. But then combining with the product rule, which holds also for such vector functions, interestingly, and very nice to know that it holds. Okay, so starting out, just rewriting this as a regular potential expression, taking 1 plus t squared in parentheses and then power negative 1 over 2. You know where it comes from. The 1/2 is for the square root and the negative sign is for the reciprocal. Now this one differentiated by the usual, by the way, using also the chain rule, results to exponent as a factor, negative 1/2, times the same expression and exponent reduced by 1, so power negative 3 over 2. And then I have to, not to forget, to put the inner derivative as a factor, where the inner derivative is the one disappears, it's additive constant, but t squared differentiated for t equals 2t, of course, okay, 2t. So that's it. And then I can put this in if I want, yes. I can cancel out this 1/2 against factor of 2, and then I have all together, and I pull this factor of t before the parenthesis, so I get negative t times parenthesis term 1 minus t squared power negative 3 over 2. That's done. So we will use this shortly. So now, for us to keep our oversight here, let's concentrate on the first component of the u roof dot vector. No, sorry, of the u roof dot. The u roof vector. So what I do first is I just construct the t derivative of the first component. That's what I wanted to say. So, and since I use the product rule, I will differentiate the scalar prefactor first, which I've done here, and use it here. And then I leave alone the vector component as to be cosine of t minus t times sine of t. And next time, other way around, plus leaving untouched the scalar term, but still writing it down in potential notation. So as it is, okay, and I don't have to read it, times, and this time I have to differentiate this just regularly after t. So here I get negative sine of t, then product rule again, minus, I should use parentheses in mind, so minus, this differentiated times this one is sine of t, minus the other way around would be minus t times minus cosine of t. So if you regard the signs and remove your parentheses in mind, I hope you get it. It will be a minus. Okay, in the end, it's a minus t times cosine of t. You can check it. It's true. It would be something like this. Okay, plus originally because minus. Let me see. Sine differentiated gets cosine. I'm sorry, I just explained it in the wrong way. Okay, it's more easy. I just use this minus for both terms. The first contribution is sine of t, the second one is t times cosine of t, but both of them must be subtracted, so I have a minus and a minus, that's it. Okay, sorry. So I can put these two together to be negative 2 times sine of t. And so also we want to know because otherwise it's too complicated, which is the value of this unit tangent vector at t equals 2 pi. And then showing that this is orthogonal to the unit tangent vector itself at 2 pi. This is just an example for the fact that the derivative of a unit tangent vector function is always and everywhere orthogonal to the unit tangent vector itself. And this is an important, well, feature which you should understand if we go back to the curve here, just for now. If I reduce these orange vectors to their unit vectors, I would ask the question, in which amount does the curve turn around? Leaving away the question in which amount does the speed, you could say, grow around the curve, along the curve. You see what I mean? So the question is, what is the rate of change of a unit vector? Here you see the unit tangent vector at 2 pi. And the answer to this question is, since a unit vector can only change by rotating, it does actually, but from point to point it rotates, you see. It means that locally, the rate of change of this unit tangent vector will always be perpendicular to the unit tangent vector itself. That's the important message behind this whole consideration. It's a little hard to understand, but think of the arrow of a clock which just turns around. This is what a unit vector does. It's unable to stretch or to be stretched or shrinked. So it can only turn around. It's a fact, a mathematical fact. Can also be visualized a little bit more. So now let's keep this in mind and then insert 2 pi for t right now, so that we have the following. Where am I? I'm sorry, I lost my focus again. I'm here. So I insert, it was my final form. Well, by now it's this one. Negative 2 pi, you see, 1 times 4 times pi squared again, power negative 3/2, just inserting. And the cosine of 2 pi is 1, of course, while the sine of pi is 0, so that makes things a little bit easier. I'm sorry, I don't know where to look here. This one plus 1 plus, where does it come from? I'm sorry. Okay, so this is just a plain 1, right? Cosine of 2 pi equals 1. This sine of 2 pi gets 0. So this is just a factor of 1. So that's all I get here. And then I can proceed to the next term, which is then 1 plus, again, 4 pi squared, power negative 1/2. And this time, the value of here inside, look at here, is 0 again before here. And this time 0 here, negative 2 times sine of 2 pi, 0. And then negative 2 pi times cosine of 2 pi, so which is negative 2 pi overall. This is a factor of negative 2 pi. And actually, we may simplify this a little bit. Because as you see, this is negative 2 pi times parentheses term power negative 3/2 still. But the same term, you could say negative 2 pi times this parentheses term is to be seen here. Okay, be careful now following this. The problem is, here the exponential is, the exponent is negative 1/2, here it's negative 3/2. So if I multiply this one, this one with the whole parentheses term again, I get parentheses term power negative 3/2 plus 1, which is power negative 1/2. So that's why I'm able to put this whole term outside the new parentheses, negative 2 pi times parentheses term power negative 3/2, then times 1, this one is for the first contribution, plus, and now the whole parentheses term times itself power negative 3/2. If I take this, look here, and multiply it with this one, I get this. And also the factor of negative 2 pi is already used here. So that's a little hard to see. Perhaps you could take more steps to find it, but in the end you got 1 plus 1 here, which is 2, plus 4 pi squared, and that's really true. It's equal to negative 2 pi times, and then I may put this to make it more visible or better or clearly recognizable. I can put this in a fractional form where 2 plus 4 pi squared is the numerator, and the parentheses term power positive 3/2 is the denominator. So that's a possible way of yes, notating the result for the first component of the differentiated unit tangent vector. It's really complicated. Now for the second one, same procedure. Okay, you remember this was the derivative of the scalar prefactor first, then times the original second component of our vector due to the product rule, and then next again the original scalar prefactor times the differentiated second component, which is now sine of t, differentiated is cosine of t. Now here again the product rule, which gets cosine of t plus t times derivative of cosine of t. Now this time it's really a minus behind, plus before, minus behind, t times sine of t. This is nothing new. And then this time I can put these two together, which is positive 2 times cosine of t. It stays negative, it stays minus t times sine of t. So, and then finally, I can insert 2 pi for t also here, and it's similar. So carefully look what I'm doing. It's again here a factor of negative 2 pi, then the same parentheses term as before, the same exponent, negative 3/2, and this time I get my sine of 2 pi 0 and plus 2 pi times 1, so I get positive 2 pi as a factor, which corresponds to the parentheses term here. That's all. And then the next contribution is plus parentheses term power negative 1/2, which is 1 plus 4 pi squared power negative 1/2. And this time I get 2 times the cosine of 2 pi, which is 2 times 1 equals 2. This is a factor of 2, while this one disappears. Okay, and then we can do something similar as before. Now I think it's even easier. If you look here, I get negative 2 pi times 2 pi. If I combine these two, I have a factor of negative 4 pi squared, and still these parentheses term power negative 3/2. Okay, and then plus, now pulling the 2 as a factor to this place 2 times the parentheses term. Ah, that's interesting, is it? Or did I forget something? I don't really, something's wrong. I think I've just forgot. Yeah, I'm quite sure I forgot the exponent here, didn't I? Is it exponent negative 1/2? Let's check it, because also here, it must be possible. Oh, I think I forgot the parentheses. That's it. I'm really sorry. I would have to put this in parentheses, and then it fits again. But this would mean, yeah. Now, if you multiply, you see this results to the first contribution, and this here behind is again the parent. The parentheses power 1 times the parentheses power negative 3/2 results to parentheses power negative 1/2, which is this one, and also the factor of 2. So everything's correct now. It's possible now to put it in fractional form again, 1 plus 4 pi squared in parentheses power 3/2. And what remains in the denominator, look here in the numerator, it's negative 4 pi squared plus 2 times 4 pi squared here. Okay, so it's 8 pi squared minus 4 pi squared, which is positive 4 pi squared, and also plus 2 times 1 plus 2. So that's, I know it's really a hard task this time, okay? But actually, in the end, what we've shown is, look here, compare these two. The first component is negative 2 pi times this fraction, while the second component is just this fraction. So I can just put this in a vectorial form, both components together, with this prefactor, our fraction there, times negative 2 pi for the first component and 1 for the second. And this is our really hardly elaborated result for the fact that the u-roof dot tangential vector at 2 pi is perpendicular to the u-roof tangent vector itself, which is the unit tangent vector at this position. You know why it's perpendicular? That's easy, because the prefactor is not important to this end. It's important that this one points in this direction and that one in that direction. And since the scalar product of these two vectors equals 0, you know, negative 2 pi plus times 1 plus 1 times 2 pi equals 0, that's an easy trick to construct two vectors in the plane which are perpendicular to each other. Just exchange the components and change the sign with one of them. So that's, in the end, the proof that what's seen graphically here and looks so harmless, this one, violet and red, that these two are perpendicular to each other. It was a hard task to find this out, I'm sorry. But then it's done.